So I was looking for a more general like theorem or paper that discussed how Selberg type zeta functions can collapse into Ihara zeta functions. And I was looking at this because, and I'm coming at this based on this like object, the MathCal I, the interface construction. So it can be shown that this collapses to a quantum graph, actually an equal length quantum graph, because all the edges are equal length L. And this is not like a regular normal surface. This is a graph-like manifold. In the graph-like manifold sense, it's not particularly like smooth manifold sense. So don't get confused about that. If we have a collar around enlarged, and then we shrink it around the graph, so we kind of collapse, localize the waves / eigenmodes, and they get collapsed onto the graph itself. So essentially the surface dynamics limit to this metric graph, this metric quantum graph gamma. And we could, use Kirchhoff vertex conditions or delta conditions. So I was basically wondering, like, how does this actually occur when you shrink the collar around the graph and it collapses, the waves localized to the graph. And I think you can study like a one-dimensional Schrodinger equation on this quantum graph. I think people do that in some areas of quantum chemistry. But anyway, to make a long story short, I did find a paper on the archive, a recent paper from December 2024, and here it is. So the title is Selberg, Ihara, and Berkovich. They say, we use a Selberg zeta function to study the limit behavior of resonances in a degenerating family of Kleinian-Schottky groups. We proved that after suitable rescaling, the Selberg zeta functions converge to the Ihara zeta function of a limiting finite graph associated to the relevant non-Archimedean Schottky group acting on the Berkovich projective line, blah, 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 blah.